All right, everyone, in this video, I'd like to talk about non-uniform accelerated motion. Again, this is something that we really didn't deal with last year because really you need some calculus in order to answer questions or to solve problems or just to graphically depict objects moving with non-uniform accelerated motion. Please know by now, it's assumed that you have this knowledge. If you have uniformly accelerated motion, ignore that when it hit the motion detector. This is uniformly accelerated motion. The position versus time graph is always quadratic. The velocity versus time graph is always linear. The acceleration versus time graph is always a horizontal line. Okay, we need to understand that as we move on. So please make sure you understand that. If you don't, please use the previous videos and the other resources that I've given you on my Canvas page. But a typical problem dealing with motion that's not under non-uniform accelerated motion is like this. So let's say, and just so you know, most accelerated motion that we do experience on a daily basis is not uniformly accelerated. It's only in very precise conditions, like if you're sliding down a hill and that hill doesn't change its slope at all, its actual physical slope at all. If you're in your car and you put your foot down on the gas and you keep your foot down at just the same distance, then you'll have largely uniform acceleration. But if you change the degree at which you're depressing your foot on the gas pedal and then you take your foot off the gas and then you hit the brakes, maybe gently at first, but then more forcefully, your acceleration is going to change throughout that. And then in the time between when you take your foot off the gas and put it on the brake, in the absence of air resistance and friction, all the friction forces involved, then you would actually be traveling with zero acceleration. So things constantly change. If you're going down a roller coaster, you know, roller coasters don't start and then have a constant slope, right? A real roller coaster is the physical slope is going to change and it'll go through loops and stuff. The acceleration of the roller coaster car is going to change throughout that entire motion. So it is imperative that we understand how to deal with non-uniform accelerated motion. So I'm gonna go over an example problem to illustrate the process by which that you'll use to describe or to solve problems for non-uniform accelerated motion. So your typical problem says something like this. A particle's position is modeled by the position function x of t equals 3t cubed plus 4t squared minus t plus 42. Now you should recognize this is not a parabola. This is not a quadratic equation. Therefore, this is not uniformly accelerated motion. If we have UAM, if the object is undergoing UAM, then the position function will necessarily be a quadratic. This is not a quadratic, it's a cubic, therefore the acceleration will be changing. All right, so part A says, where is the particle located at t equals 2 seconds? This you could actually answer without calculus. You don't need calculus to answer this question because x of t, our position as a function of time, tells us exactly where the particle will be located, right? Position as a function of time. At time t equals 2 seconds, if I want to know where the particle is, then I actually want to know what the position is. So for part A, all I need to do is substitute in my function, I just need to evaluate my position function for t equals 2 seconds. So I just evaluate my position function at 2 seconds. So I'll get 3 times 2 cubed plus 4 times 2 squared minus 2 plus 42. And then I just evaluate that. If you're like me, you don't skip steps and you don't tend to make mistakes when you're doing this kind of a problem. So I'm actually going to use PEMDAS and evaluate this one step at a time. So I'm going to square the 2. So I get 3, I'm going to cube the 2. 3 times 8 plus, and then I square the 2 here, 4 times 4 minus 2 plus 42. 3 times 8, I think, is 24. 4 times 4, 16. 2 is the same. 42 is the same. And then I just add all these up. 24 plus 16, that's 30, that's 40. Minus 2 plus 42. 40 minus 2 is 38 plus 42. And that should be 80. And if we're using our standard SI units, this would be in meters. So my position evaluated by the function, using the function at 2 seconds, tells me that the particle will be at the 80 meter mark in our coordinate system. And again, we're just talking about a number line, an x-axis number line, the position of the particle on the x-axis number line. This is one-dimensional motion. And so our position at 2 seconds would be 80 meters, okay? So that's just evaluating a function at a particular x value, or a particular t value in this case, since we're doing physics. Not difficult to do. Really, any algebra, anyone with a little bit of algebra knowledge knows how to do that. Just replace the y with x and replace the x with t for time. All right. Number B is where we actually have to start throwing some calculus. Because number B says, what is the particle's velocity at t equals 1 second? Well, this is a position function. With the position function, I can't know the velocity unless I do the derivative. Remember, the derivative of the position function is the velocity function. So to start this problem, number B, I actually first need to determine the velocity function for this object. So if my position function is x of t equals 3t cubed plus 4t squared minus t plus 42, then to get my velocity function, I need to find the derivative. So my velocity function is the derivative with respect to time of my position function. I'm going to change up the way that I notate the derivative here just so you get used to seeing it in so many different forms. So this just says the derivative with respect to time of my position function is going to be equal to, hopefully at this point, the derivative using the power rule is becoming a little easier, and the sum and difference rule and the constant multiple rule just say I do each one individually. The constants I don't really deal with in the derivative. I just multiply my result by those. So here I'm gonna bring down the 3, multiply it by that 3 in the front, and then I'll end up with t to 1 less degree in the exponent. So this will end up be 3 times 3 is 9 times t to the second power. Right here, bring down the 2, multiply it by the 4, so I get plus 8 times t to the first power, which is just t, minus the exponent here, you bring down the 1 times t to the 0 power, so that's just going to be minus 1. Right, the derivative of x with respect to, the derivative of y with respect to x of just like x, it's just 1, okay? And then the derivative of a constant is 0. So that tells me my velocity of time, versus my velocity as a function of time is going to be 9t squared plus 8t minus 1. There's my velocity function. It is the derivative of the position function. Notice using these rules makes the derivative of polynomials pretty easy. Try to do this derivative using the limit definition and have fun. That would take up more than what I have up here at the board. It just requires a lot of algebra. You're actually going to have to, try it and you'll see what I mean. Using the rules makes it a lot easier, but again, please remember that in your calculus class, you can't use these rules until your calculus teacher says it's okay. And that's for a reason, because you're going to gain much more insight into the theoretical mathematics behind the derivative from your calculus teacher. You get much more insight from your calculus class than you will in your physics class. We just use the derivative as a tool to do physics. Okay. All right. But the question didn't ask what the velocity function was. The question asked what the velocity of the particle is at t equals 1 second. So I actually have to evaluate my velocity function at t equals 1 second. So I just say my velocity at t equals 1 second. So the velocity function evaluated at t equals 1 will be 9 times 1 squared plus 8 times 1 minus 1. So that's going to be 9 times 1 squared is just 1. So that's going to be 9. 8 times 1 is 8 minus 1. So that's going to be 9 plus 8 is 17, I think. Minus 1 is 16. So the velocity of the object at 1 second will be 16 meters per second. Again, we would not have been able to answer this question last year using algebra. Calculus is required for this type of a question. The derivative is definitely required. This is why we need to cover the derivative so early in AP Physics C, because we need to describe the motions of objects undergoing non-uniform accelerated motion early in AP Physics C. Okay? All right, so that was part B. So let's move on to part C. Part C says, what is the particle's acceleration at t equals 3 seconds? Well, hopefully realize now, remember the slope on a velocity time graph is acceleration. Therefore, the derivative of a velocity function is the object's acceleration function. And so if I have this velocity function, let me rewrite it up here. It is the velocity as a function of time will be 9t squared plus 8t minus 1. Then the acceleration function the acceleration as a function of time will be, and I'll use a different notation for the derivative. You can say the derivative of the velocity with respect to time, or that's usually pronounced like dv dt, dy dx if you're in your calculus class. Same thing as this, it's just using a slightly different symbols to indicate the derivative, but this does represent the derivative of the velocity function with respect to time. Again, just bring the 2 down in front, multiply it by the 9, you get 18 times t to the 2 minus 1 power, so that's t to the first power. And then you bring the 1 on the exponent for the t down, multiply it by the 8, which is just 8, times t to the 1 minus 1, or t to the 0 power. So that's just going to be 8. And then the derivative of that constant negative 1 at the end is 0. Okay. So there's my acceleration function. My acceleration as a function of time is simply going to be 18 times t plus 8. And the question says, what is the particle's acceleration at t equals 3 seconds? Well, then I just evaluate my acceleration function at time t equals 3. So that's going to be 18 times 3 plus 8. And 18 times 3 should be able to do in my head, but I don't want to mess up, so I'm not going to do it in my head. That's going to be 54. And then I add 8 to that, so my acceleration at 3 seconds will be 54 plus 8, that is 62 meters per second squared. And again, that's going to change, right? Our function, acceleration is a function of time, t does vary. The variable t is in there, and so as t changes, so will the acceleration. All right. So hopefully that makes sense. I'm going to do one more problem, but I'm going to need some more board space, so give me a second to erase. And I'm going to leave my velocity function up there because we're actually going to need it. Now this question, the last question, this is kind of a tricky one. It's not quite as straightforward as the others, but you do have the tools necessary to do this problem. The question says, at what times is the particle motionless? Well, it's going to be motionless when it obviously stands still. If we're talking uniform accelerated motion like this cart, there's only one time, right there, where the cart's motionless. And so, right there, motionless. So this question is saying if we have this particle whose motion is described by this cubic function, if that particle, again, is undergoing non-uniform accelerated motion, it's probably going to reverse direction. It's probably going to stop at some points and then resume maybe in the other direction, maybe back in the direction it came. And we want to find out what that is. To answer this question, we actually don't need any more calculus because we have our velocity function. And since we're looking for when the velocity is 0, essentially, we're looking for when the particle's motionless, that's what we're looking for. When is the particle's velocity 0? So the velocity as a function of time has to be 0, right? That's what motionless means. And since our function is 9t squared plus 8 minus 1, then all we need to do, what we've already done, is set the equation, the function, equal to 0. If this is what models our velocity function, all we need to do is set it equal to 0 and solve that equation for t. Those time values, those t values, will tell us what times the object is at rest. So really, I just have 9t squared plus 8 minus 1 equals 0. Now in this class, you're free to use this. T equals negative b plus or minus the square root of b squared minus 4ac all over 2a. You can use the quadratic formula in this class if you'd like. However, this is not a math class, this is a physics class, and so you can use technology to use this. I'm actually not going to use the quadratic formula. I'm going to use some technology to handle this, and if I was doing things right, I would have had this pulled up already. Give me 1 second. You're free to use any quadratic solver. You have quadratic solvers in your calculators. You can use quadratic solvers that you might find online. This is one that I tend to use quite often when I need to solve a quadratic. And you might have asked before, let me write this off to the slide. You might have asked before, why do we solve quadratics? Why do you have to learn them? Well, if you're doing physics, we find that quadratics pop up quite a bit. And so solving those equations is pretty important. So I have 9t squared plus 8 minus 1 equals 0. Again, you don't need to use the quadratic formula here. You can use your calculators or you can use any kind of computer program that has a quadratic solver. I'm fine with that. In this particular one, it's mathisfun.com/quadratic equation solver. You just put in the coefficients. So my t squared term has a coefficient of 9. My t term has a coefficient of, oh, that's 8t, sorry. Has a coefficient of 8. And my constant term is a -1. And I hit enter, and I get roots of -1. So I get a time of -1 second and 0.111 repeating seconds. Don't use a little line over it. If you put a line over the 1, then that means that you know exactly that value is 0.11111 off to infinity. We're fine with just 3 digits in this class. That's fine. Now, -1 seconds, if we start the object's motion at time t equals 0, then at t equals -1, the object was not at rest because well, I guess technically it was, but that's not really described by the physics. So very often we throw out the negative values for time. Unless we start our stopwatch in the middle of the object's motion. And if we start it in the middle of the object's motion, then we would say, well, a second before I hit start on my stopwatch, then the object would be at rest. But in this case, if we started the object at time t equals 0, this would be an extraneous solution. We would not need it. And we would just say that the time that the object was at rest is 0.111 seconds. Right? So that's how you'd solve that kind of question based on a position function. At what time is the particle at rest? You just find the velocity function, set that velocity function equal to 0, and solve for time. All right, that's about it.